So let's do an example here. Suppose, let's take an example with a continuous case. Let's suppose that the joint density function for x and y is, I don't know, say 2/3 for x and y points in some region that we'll call A. Okay, 0 otherwise. And so I'll draw a little picture of that. Here's my region A. I'm going to say this is 1, this is my x-axis, and here's my y-axis. And here's 1, 2, like this. And I'll go zippity-doo, A, like this, right? This right here is the region I'm going to call A. This is the region. Whoops. This is the region that I'm going to call A. Okay. So this density function is actually, it's constant, right? And it's sitting up here. It's sitting up here. Up out of the page. It's like up here. It's closer to your eyeball, right? It's up in here somewhere. And then it's 0 down here in the paper. Okay? It's 0 down here in the paper. Oh, and by the way, we have to stipulate the boundary here. Even though the chance that that point's going to fall on the boundary is actually 0, let's just say A is the collection of all the points that are on this boundary or in its interior. Okay? Is that okay? So A is a sort of a closed shape. Contains all of its boundary points and all of its interior points. So the question is, are x and y independent? Are x and y independent? Okay? That is, if you throw a dart at random into this, somewhere in this region A, and it lands uniformly in A, does its x-coordinate have anything to do with its y-coordinate? Well, I can tell you just by looking at the picture, the answer is, drum roll please, yes. The x-coordinate does have something to do with its y-coordinate. So actually the answer to this question is big fat no. They're not independent. See, if x, let's say x falls down here, then where can y fall? Y is going to fall somewhere in here, right? But if I move x, if I say, hey, guess what? Condition that x falls over here. Now, what is the behavior of y? Y behaves something like, I don't know, it can be somewhere in this region, right? Between 1 and between like 0 and 1 3/4. See that? So the value of the x-coordinate has can change the possible values for the y-coordinate. Alrighty? But now let's work with this. Let's take a look at the marginal density function for x. So we've already got the joint density function here. What I'm going to do is I'm going to go ahead and get the marginal density function for x and the marginal density function for y and multiply them and see if it is in fact this. The answer should be no. They should not be equal, right? Because up here, x and y are going to be independent if and only if this happens. All right, so let's get the marginal density function for x. I know that this is just the integral over the reals of the joint density function for x and y, dy, right? And just basically integrating out the y stuff, if you can, if that terminology even makes any sense. Okay, so this is integral over the reals of 2/3 times the indicator that x and y is in a region called A, right? And dy, right? I'm going to integrate out the y. I'm going to be left with a function of x, which is exactly what I need, right? It's a function of x. Okay, so now what happens when I do this? So I got 2/3 out there. I have the integral like this. This is 1 in this region called A. Where is y running from? Y goes from, what are you running from, y? It's running from 0 up to this line, right? y goes from 0 up to this line. It is indeed a function of x, right? Where that limit of integration for y. What is this? Let's see. The intercept is 1, and then the slope is also 1. So this is the line 1 plus x. Y goes from 0 up to 1 plus x, doesn't it? Yes, it does. Okay. So then I just have dy there, right? Okay. And this actually, I need to multiply the whole thing by the indicator function that x is between 0 and 1. X between 0 and 1, I guess. Okay, so all this becomes 2/3 times y from 0 to 1 plus x, indicator that x is between 0 and 1. So then this is just 2/3 times 1 plus x times the indicator that x is between 0 and 1. Okay, this is the marginal density for x. Let's now get the marginal density function for y, right? Just to remind you, what we want to do is get the two marginals, multiply them, and see and test whether or not we get the joint. Okay, so I'm going to do the same kind of deal here, but sort of integrate out the x variable, like so, right? Okay. Let's see. So our density function there, remember, was 2/3 times the indicator that x and y are in the region A, and integrating with respect to x there. Okay. And so this is going to be 2/3 integral, let's see, where does x go? I'm going to have to look at the picture here. X goes, see, this way, we're integrating out the x. X goes from here to here, right? Careful, now look, x goes from 0 to 1, all down here in this square, right? Down here in this square. It goes from 0 to 1, 0 to 1, 0 to 1. But up here, it does not. It goes from this line to 1. What is this line? X is going from let's see, this is the line y equals 1 plus x, right? This is the line that y equals 1 plus x. So x is actually going from y minus 1 up to 1 here, right? For example, if y is 1, then x is 0. If y is 1.5, y is 1.5. 1.5 minus 1 is 1/2. And so x is going from 1/2 to 1. See that? So what I'm going to do now, when I'm running this way, left to right, for this shape, I'm going to carve it into two pieces. A square, which is pretty nice, and a triangle, which is also pretty nice. Okay? So I'm going to have two integrals here. Okay? I'm going to integrate this first one. You see the x goes from 0 to 1. So it goes from 0 to 1. This will be for y in 0 to 1, right? If y is between 0 and 1, then this is going to be 2/3 integral from 0 to 1. dx, which comes out to be, what is that, just 2/3, I think. On the other hand, if y is between, say, 1 and 2, then what have we got? We have 2/3, whoops, 2/3, again, dx, but this time, remember our x value is going to go from y minus 1 up to 1, okay? So what does that come out to be? That's 2/3 times 1 minus y minus 1, okay? Or 2/3 times 2 minus y, right? For y in 1 to 2. And of course, it's 0 otherwise, right? For any y outside of that interval from 0 up to 2. Okay. So now, our test is, we want to see if this is true, if this is equal to if the joint density can be equal to the product of the marginals. Is that true? Well, no, it's not. For example, let's say you pick x and y in the unit square there, from 0 to 1 to 0 to 1. Then in this case, what's the product of the marginals? Well, let's see. F sub x of x is was this stuff, right, for x down there. And so that's 2/3 times 1 plus x. It's going to be 2/3 times 1 plus x. And then times f sub y of y in there, that was in that region, that's 2/3. So it's times 2/3. Okay. So this is 4/9 times 1 plus x, which is not equal to, in fact, 2/3, which is f sub x, y, x of x and y. There, in that region, just looking in the box, okay? Okay, just looking here. All right, so it's just looking in this square part, okay? They're not equal. So, x and y are not independent, just like we thought. Just like we thought.